Well, hello here. Welcome back to POE. We're going to be doing day 4 notes today over simple machines, specifically incline plane, wedge, and the screw. These are the ones that specifically that we'll be talking about. A couple things I want to remind you of, and that is that when it comes to mechanical advantage, whenever we have a mechanical advantage that is greater than 1, we're going to have less effort force and greater distance. Whenever the mechanical advantage is greater than 1, we're going to have less effort force and greater effort distance. Whenever that mechanical advantage is less than 1, such as like on a fixed pulley where we have lots of friction, we're going to have greater effort force. You're going to have to pull harder, but you're going to be able to usually do it with less effort distance. Of course, when we have our ideal mechanical advantage, we're going to be using distance. It's a theory-based calculation. And we're going to be doing our actual mechanical advantage. We're going to be using force, and it's an inquiry, meaning it's been tested. We actually have results to prove it. And it deals with forces. Efficiency. A couple things I wanted to point out to you here is that no machine is 100% efficient. Why is that? Well, primarily because of friction. I've got to pull my pin back up here again. Because of friction. We definitely, friction is what causes things to be less efficient. And that's because the actual mechanical advantage turns out to be less after the friction. And that's with all machines. Friction is going to make the actual be less. Alright, first thing we're going to discuss here then is an inclined plane. It's a flat surface on a set or at an angle or an incline with no moving parts. It's able to lift objects by pushing or pulling the load. Incline plane mechanical advantage. It's still dealing with distances. It's ideal. The difference here is the distance of the effort is the slope, and it's the length here. So in this case, the slope in this case is 15. The height is 4, so it would be 15 divided by 4, which turns out to be 3.75. That is the ideal mechanical advantage of the above plane. Now, when we take a look at the actual mechanical advantage, it's still going to be the same thing. It's the forces. The actual is going to be the forces. And that still gives us then the resistance. They tell us up here is 50. Get a pen up here again. Up here is our resistance of 50, and here they tell us it's our effort. So the actual mechanical advantage is going to be 50 over 20, which is 2.5. So on the bottom, we're going to get 2.5. On the top, we get 3.75. And when we divide those, we get, I have those in the wrong spot again, don't I? Lost that off. 2.5 divided by 3.75. And as most of you can tell, probably already know, there was a reason why I knew that wasn't going to be correct, because my answer was going to be greater than 1. And we know that all machines have to have an efficiency that is less than 1. But we're flying right through these notes here today. The next thing I'll talk about here is a wedge. It's a function as a moving inclined plane. Tapers to a thin edge and is used for splitting, raising heavy bodies, or for tightening by being driven into something. Here they drive it in, and it widens the piece of wood. So it's used at the top of a lot of axes and wedges, and that's why we call it a wedge. The ideal mechanical advantage. It's very similar to an inclined plane, except we have the height, which is the perpendicular, the part that would be hit or smacked, and then it's just the overall length of it. So in this case, what is the ideal mechanical advantage of this one? Well, it's going to be 10 divided by 3. That's 10 divided by 3, or the ideal mechanical advantage would be 3.33 repeating. And that's all there is to that one. Okay, let's talk about the screw. Screw is an inclined plane wrapped around a cylinder forming the path and pitch. As you can see here, here's the path it's chosen, and then the pitch is the distance between the two. A wheel and axle used to create the rotary motion. So right here we have the wheel, and then as it's moving around here is the axle, and as it moves around it gives us that wheel type action. Properties. It's used to change rotary motion into linear motion. It's used as a threaded fastener. You get large mechanical advantage from it, and there's a large amount of friction loss. There's going to be a lot of friction with the screw. Okay, ideal mechanical advantage. The distance of the effort, it's how far am I actually going to have to turn it, and that would be just simply the circumference. And then the distance of the resistance was every time I turn it around one time, how far does the screw go down? And that's the pitch. The pitch is the distance between them. So our pitch would be from there to there, two different threads. All right, the pitch is the distance between two threads, and that's, it's still dealing with distance here. So in this case, they want to know what is the ideal mechanical advantage of the screw above if its effort applied by an 8-inch long wrench. So we have an 8-inch long wrench. So the circumference is going to be 2 pi r, or 2 times pi times an 8-inch wrench. And up here, they're telling us it's a quarter 20 NC. So every, just one second. So this first bit of information up here, this 1/4, tells us what the pitch is. So that's going to be 0.25 down here. So on top, we're going to get 16 times 3.14, which gives us 50.24. And as you can see, we're going to get an incredible amount of ideal mechanical advantage. It's going to be real close to 101. I'm not going to take time to actually punch it into the calculator, but it's going to be really close to 101 is the ideal mechanical advantage. Now the actual mechanical advantage is going to be the force it takes to the resistance, and the effort force then would be the what's going to go on the bottom. So as we go about trying to calculate this one, this is the actual. Well, my resistance is going to be 1,200 pounds, and my effort it takes to turn with that 8-inch wrench is going to be 35. So we get 1,200 divided by 35, and we get an actual mechanical advantage here of about 34.3. The efficiency then is going to be 34.3 over 101. And as you can tell, that's going to be very close to about 33 to 34%. Now, what I want to point out too is why is it so low? Well, as we looked at it earlier, and we told you, or I told you, there's a large amount of friction loss. Large amount of friction loss. And because of that large amount of friction loss, all that friction is what affects the efficiency. And because we're losing all of that, what we're really losing here is energy. It's energy that's being wasted or lost to, those of you who are in physics will understand this, but the thermal energy, it's being transferred in the friction. We're not being able to use it as a part of this machine. The last thing I want to go over here then is compound machines. Compound machines, we can calculate these mechanical advantages simply by multiplying them. So if we had several machines going on, we would just calculate the mechanical advantage of one, calculate the mechanical advantage of the second one, and then multiply it by the mechanical advantage of the third, just like we do with a pulley.